Hello, I'm Gareth, and my talk today is going to be about our attempts to measure deformation between the San Francisco Bay Area and the Sacramento-San Joaquin Delta area. I'll just call it the Delta. Um, this is work that I've been working on with Mike Floyd from MIT, and thank you to the conveners of the session for inviting me to talk. The picture you can see here is of Montezuma Slough from last September, when we were on our last field campaign in this area. This is a GPS receiver, a GNSS receiver that we set up overlooking the slough on a bridge abutment, which is a nice stable benchmark. I remember this day very well because it was 114 degrees, and we concentrated very strongly on our hydration this day. We made it through alive. Why are we interested in this? It turns out that an earthquake in this area could be very, very dangerous. It could pose a large risk to the whole state of California. This is a picture or a screen grab of the California Department of Water Resources website. And this quote is from the first paragraph that lays out how the Delta is the hub of California's water supply. It supplies fresh water to 2/3 of the state's population, mostly in the large population areas in Southern California and the Bay Area, and also to millions of acres of farmland. If an earthquake happened that disrupted this water supply, the results could be catastrophic to the state. This is a picture or a figure that I've made showing the active faults in California, these red lines and these pink ones, and also the areas of liquefaction. These are highlighted in pink. The delta is here, and you can see that within the delta is a significant amount of land which is at high risk of liquefaction. Most of the channels and levees in here that you can see here would be at risk, and the only reason that more of this area isn't covered in pink is that the data set I plotted ends right at the edge of the 9 counties of the Bay Area, which end here. I would anticipate that nearly all of the delta would be at risk. Zooming in a little, the major fault that is inferred to exist here is the Midland Fault. This is found in seismic reflection profiles that were collected for gas exploration in the 80s, and it's mapped through most of the delta. Obviously, if an earthquake happened on this fault, it could be a magnitude 6 or larger, and that would generate large shaking in the area, which would also induce liquefaction. So one thing that we really want to understand is how much strain is accumulating in this area and how much is accumulating on the Midland Fault that could drive a future earthquake. And that is why we have been measuring with GNSS the strain across this area. We're not the first people to work in this area, broadly speaking. This is a figure from a paper by Will Prescott from the early 2000s, and it shows the plate boundary normal velocity. So if you drew a profile from Point Reyes to the Great Valley through Davis, more or less, that's where it goes, and measured the displacement along, or the velocity along that profile, this is what you get. So there's about 4 millimeters a year of total difference between the plate boundary zone, which starts at the Farallon Islands and heads basically to the edge of the Coast Ranges, between that zone and the Great Valley block, which includes Davis and most of the small towns in the Great Valley. There's about 4 millimeters a year of relative displacement between those two places, and that is manifest across a zone about 30 kilometers wide. So this implies that there's shortening across this zone that might drive thrust faulting, and the Midland Fault is inferred to be a reverse fault. So can we improve on the resolution of the data that you could collect in this area? Could we see how extensive and how concentrated this convergent zone is? Can we identify it? Can we localize it to faults? That is why we are interested in doing GNSS field work in this part of the world. We've been measuring velocities in this region since 2008. A group from UCR with collaborations with Mike Floyd at MIT and with the help of lots of field assistants. This is our data set. This also includes data collected by the USGS and also data from continuous stations. Our intent for measuring this was to understand the plate boundary parallel velocities and the slip rates of the major active faults in this area. And we have modeled them, and basically the deformation you can see here can be fit by 3 major fault systems through here: San Andreas, Rogers Creek, Markham, and the Green Valley fault system. And that accounts for nearly all the deformation you see in this map. And while that's great for studying the most active faults in the region, obviously, if we're interested in studying deformation in this area, the delta, we have a big hole to fill. And our next thing to do is to try and figure out how to fill that gap. To add new velocities to our map, we need to measure sites that already have GNSS measurements made at them. Luckily for us, the California Department of Water Resources had made 2 campaigns in 2011 and 2017 at all these sites marked by triangles. So in order for us to get new velocity estimates, we picked a subset of these sites and went and remeasured them again in the summer of 22. However, one concern was that many of the benchmarks were in sites that may not give you a measurement that is actually diagnostic or representative of the motion of the crust, rather a motion that's non-tectonic. We know this is an issue because the levees in the Sacramento Delta area have been known to be subsiding for quite some time. This area was formerly a tidal marsh, and there accumulated a great thickness of peat in these areas, and that peat over time has been oxidizing through microbial action and releasing CO2. So the carbon in the peat is basically being expelled as gas, which means that over time the amount of mass in the levee system is reducing, and the fear is that this will cause maybe the levees to fail all on their own, even without an earthquake. But of course, the fluid saturated substrate and the mud and everything else that's in here makes it also much more susceptible to liquefaction. But a fear is that if we do GNSS measurements in this area, then we might just be measuring the movement of the levee and not the movement of the crust underneath it. This fear is not unfounded. This is a Google Street View picture of a road in the Sacramento Delta area, and you can see that the road is full of cracks and repairs, and it was actually this side of the road when I drove on it was several inches higher than the other side of the road. It was quite gnarly. These are classic signs of lateral spreading. This is outward motion that's stretching the road and breaking it. And if we were to make measurements here, maybe that's what we would be measuring and not the movement of the crust underneath. This is just another picture gratuitously showing the location of a survey benchmark. It's actually over here. We found it, but we declined to measure it because you could see in the road there are all these cracks again, and this road surface is broken up completely. This is another area where lateral spreading is occurring. So we had to figure out a way of selecting which sites we were going to measure without subjecting ourselves to maybe collecting things that would not be useful in the long run. And so what we used to solve this problem was INSAR. INSAR, of course, I like to talk about it, is a technique that can measure deformation over large areas. It's a satellite-based remote sensing technique. And in this particular case, and what I'm going to show you here, is that you can actually use it to show areas that are affected by subsidence that is not tectonic. So I've been working with Sim Sanger, who's pictured here, from JPL for several years now to produce these maps in a SCEC-funded project called the Community Geodetic Model. I guess the novelty here is that we were using standard product interferograms, which were produced by JPL, basically processed INSAR data so that you can use the data without having to process it. And then we just solved for the best fitting velocities from a stack of interferograms. And this is what they look like. So I've got shown at the top are the velocities and the bottom are the uncertainties. And you can see we have the whole state of California is covered here, but it's shown in this kind of exploded view because these tracks overlap. So yeah, California isn't really this wide, but California is covered by 9 tracks of the Sentinel-1 satellite. And in these images, blue colors mean the ground is moving relatively away from the satellite. The satellite line of sight is shown by these pink arrows. If you see the same feature, the same color in both the ascending and descending data sets, that generally means the ground is moving vertically. And if it's blue in both set data sets, it's moving vertically away. So this blue thing here is the agricultural part of the Central Valley, which is subsiding due to groundwater extraction, we think. You can see that the San Andreas Fault is marked as a very abrupt change in velocity, which changes sign between the two data sets. That means it's moving horizontally. That's the creep on the San Andreas. But for the purposes of this talk, the pertinent feature is this area out here, the delta, where the majority of the velocities are bluer than their surroundings, which means again that the ground is moving downwards, and this is a signature of the subsidence in that area. Zooming in a little, showing this INSAR data again at the ascending track, which is not very sensitive to fault parallel movement. So it's showing nearly everything you can see here is vertical movement. And many of the sites, as you can see, these triangles are in locations which might be subsiding. So we were careful to avoid those. And we selected a set of stations that were mostly out of the blue and to the west of the delta, and that's what we measured last summer. This is just to say, I didn't do this on my own. Mike came along, here he is, and 2 graduate students from UCR were also there. And I'm happy to say we all made it out of there alive. Having made it back to the lab with our data, we found that when we tried to process the previous campaign data, actually the 2011 data, that they were being thrown out by the processing software due to having faulty information in them. It turns out the L2 pseudo range was the same as the L1 pseudo range, which is weird and unexpected and wrong. But because Mike is a GPS processing genius, he figured out a way of getting those data processed so that we could make a velocity out of with the measurements we made in 2022. The trick was to treat them as if they were data from a codeless receiver, which, as I understand it, is a strategy that was employed in the early days of GPS. So this is old school. So having figured that out, we went from a map that had this coverage with about 15 extra stations out here in the east. What's interesting is that these sites in the east seem to have a motion which is much more northeastward at a rate of around 2 millimeters a year. It's in contrast with the sites out in the west, which seem much more plate boundary parallel. It seems you can separate the sites out in the east here from the sites out in the west by drawing on the boundary between these two domains, which corresponds very closely with the range front of the Coast Ranges, which runs up to the east of Lake Berryessa here, and see divides this into these two zones. In the west, stations are moving much more parallel to the faults and to the plate boundary in general, and this plate boundary parallel motion seems to end at the last of the major strike slip faults, the Green Valley Fault out here. Out in the east, this is a zone of more plate boundary perpendicular motion, and if you look at the trend that these stations are moving, it's actually quite close to perpendicular to the strike of the Midland Fault, suggesting indeed that the interpretations of this being a reverse fault are supported by the contemporary deformation in this area. So that is the headline result of our preliminary work in this area. It seems that the deformation in the delta appears to transition from plate boundary parallel in the west to plate boundary perpendicular in the east as you cross the Coast Ranges. The motion in the east, just to the west of the delta, is consistent with the interpretation of the Midland Fault being a reverse fault. The deformation is complicated by the non-tectonic subsidence of the delta levees. This makes it difficult to make GPS measurements or GNSS measurements that actually capture the tectonic motions. And we have hit on the strategy of using our INSAR velocity maps to help identify sites that may be more stable. Obviously, we will try to find geological associations with these stable areas and try and use the map lithologies as well as a guide to this. And we still want to do more of that because we do not yet have good deformation constraints in the east of the area. So east of the delta, we don't have any data at all at the moment. And our future goal is obviously to go and expand out there. And that's what we hope to do in our next field trips. So thank you for your attention. I want to thank a whole slew of field assistants who collected data over the years and funding from the USGS and SCEC. Thanks.